gives compared to a conventional power plant. Especially here in IGCC plant, the CO2 capture is also much simpler compared to a conventional plant. Then, if natural gas or other fuels are available when IGCC is in operation, even you can switch over to other fuels, so that flexibility will be there in an IGCC plant. So these kind of, in addition to higher efficiency and environmental power, other advantages are also there with IGCC systems. Now, I will talk about the DHL's experience on IGCC technology. Now, this program was started with an objective of utilizing these higher scores efficiently using this IGCC technology. Then, the program aimed at developing this process as well as equipment for the gasification and other subsystems. It also aimed at developing some simulation models so that we can achieve optimal system integration in IGCC mode. Then the program also aimed at developing some process technology for gas cleanup systems. This slide gives a gist of the IGCC development in DHL. That is, first, DHL started with a moving-bed-based IGCC system in Trichy unit. Because the moving-bed gasifier was well established at that time, in the 80s, only the combined, DHL wanted to test the combined cycle concept first. So the moving bed, the 6.2 megawatt capacity IGCC pilot plant with moving bed gasifier was initially set up in DHL Trichy unit, and that was successfully operated. Based on the success of that plan, but even the moving bed gasifier technology was established along with that. It was indigenously designed and established by DHL. But because it had its own drawbacks for a power generation scheme, DHL did not proceed further with that technology. In parallel, our DHL experts, as well as I told you earlier, government experts, they came to the conclusion that today's gasification technology would be more appropriate than this technology. So, in parallel, we started developing this today's gasification technology. Then, in that process, two pilot plants were set up at DHL's corporate organization in Hyderabad. One that 18 ton per day full capacity Pedu plant, that is process equipment development unit. Then one 200 test facility also was set up in Hyderabad to establish the fluid gasification process, to develop the subsystems, as well as to develop other model-related aspects for this gasification system. Then, based on the success of those today's gasification facilities in Hyderabad unit, it was scaled up to 6.0 megawatt and retrofitted into this CCDP combined cycle plant somewhere in the 1990s, and that was successfully being operated until today. So, with the success of all these developments, now DHL has geared up to set up commercial technology to develop commercial scale 180 megawatt IGCC in probably in geographical power station, if that proposal comes through. Now I will talk about each technology in detail. This is the pictorial view of the moving bed gasification plant set up in DHL Trichy unit. The tallest structure is which is housing the moving bed gasifier. Now, this moving bed gasifier was designed to process 150 ton per day coal at an operating pressure of 10 bar. At an operating pressure of 10 bar and at a gas pressure of 590 degrees centigrade. Then, in terms of performance, it it was aiming to achieve a carbon reduction of 86%. Now, if you see the design figures and actual figures, more or less all the parameters were achieved in terms of these two design parameters and actual parameters. Even the carbon conversion, even up to 91 could be achieved in some operations. And this was operated in a combined cycle also. So the main objective of this gasification plant was at time to gain experience on system integration and operation of gasifier in IGCC mode. Now this is the scheme of moving bed gasifier. This is a moving bed gasifier. Then it has got water jacketing for raising steam. Now the coal is fed from atmosphere to pressure through a lock arrangement. Then air is drawn from the gas turbine through a booster compressor. Steam is generated through this jacket. Whatever steam is generated through the jacket is utilized to heat for gasification. Then the hot gas which is coming out is cooled in a gas cooler. Then it is quenched in a quench column and brought, the temperature is brought to 100 degrees centigrade. Then all the particulates are moved here in two lines of which is cut down. Then finally the clean gas is generated in gas turbine and the power is generated. The hot exhaust gas goes through a heat for the steam generator which raises steam, and that steam is expanded through this steam turbine to generate power. So the design output, the design power output will be 6.2 megawatt. Up to 5.3 megawatt was generated in actual condition using different fuels. Now with this, the plant has logged about 5,500 hours of operation, and in that it was operated for 7 times in an IGCC mode, and it could achieve a very good coal gas efficiency of 68 to 79, and the carbon conversion efficiency up to 70 to 91%. So the objective of establishing this plant was achieved. DHL got very good hands-on experience in handling this combined cycle plant. In the system integration aspect of this IGCC plant was thoroughly understood. Then, in parallel to this development of this moving bed gasifier, the DHL again, the DHL experts came to the conclusion that the moving bed fluidized bed gasification has to be developed further, has to be developed to go for IGCC plants. So, 2 pilot plants were set up in DHL corporate office in Hyderabad. This is one such plant. It is a 200 fluid bed gasification plant at Hyderabad. This is the gasifier. Then this is the top of the gasifier going to the cyclone. Then the bottom of the gasifier with all that screw extractors to be there. So this plant was set up mainly to as an experimental facility for optimizing the operating parameters, for testing a variety of codes, and for using different cleanup systems, so that maximum information about gasification process and the subsystems can be obtained. So here you can see this candle filter was tested in this gasification unit for assessing the performance of the filter for removing the particulates up to the 2 milligram per nanometer level. Then it is a very sophisticated system. It can be operated through a computer. All instrumentations were automated. It had got one bottom system was also tested here. It has got inverse gas sampling facility for assessing the kind of conversion inside the gasifier. Then to improve the conversion much better from it. That is, initially we started with only 1-2 system. Then we found the carbon content in ash was considerably high. So maximum about 85% with one slew system. Then we thought, obviously it is not possible to go for 85% conversion and convince customers to buy this technology. So we went in for the funds recycling system to improve the efficiency for that. So that was tested in this system. We will establish that funds recycling system here, similar to loop seal COBC boiler, which is being supplied by DHL. Now this is the flow scheme of that plant. This is the gasifier. Then it has got two cyclones, a candle filter. Then this black here, this one vent. Now the kind of R&D studies conducted on this small pilot facility are listed here. That is, the optimization of reactor ratios for different fuels was carried out. Then effect of blast temperature. That is, airstream blast temperature was varied right from ambient condition to 300-350 degrees centigrade to see its effect on the gasifier conversion, the carbon conversion, as well as the improvement in calorific, gas calorific value. Then fine recycling system using loop seal. Then performance of ceramic energy filters. Then to assess the kind of fluidization which is happening in the fluidized bed. These traces studies were conducted for assessing the type of mixing which is happening in the fluidized bed. And Bob Adams Center helped us in conducting this test. Then estimation of trace contaminants in different streams. Now, these gasification-based IGCC systems has to have an inbuilt gas cleaning system, which has to be very stringent to provide clean gas to gas turbine. The gas turbine puts the stringent restriction on gas quality. So they even specify like sodium some 23 parts per billion, calcium some few billion parts per billion. Like that, contaminant concentrations are very stringent. So to assess the kind of trace contaminants which are coming in different streams, it was tested in these pilot plants. Then different fuels were tested here. That is lignite fuel, high ash, sub-interest coal, pet coke, high sulfur Assam coals. All these fuels were tested in this pilot plant to assess the suitability of the fuel for gasification process. Now this is another pilot scale facility which was set up in corporate of Hyderabad. This can gasify about 18 tons of coal per day, and the gasifier diameter was about 450 millimeters, and its operating was about 11 kg per square centimeter. This is another pictorial view of the facility in Hyderabad. This experiment facility was developed in 3 phases. In the first phase, we focused on establishing the process, then developing some suitable distributor, airstream distributor configurations, then establishing the operation methodology for gasification plants. Then the second phase, the optimization of all operating parameters were adopted. In the third phase, the operational elevated pressure and operational reliability for long duration operations were tested in these plants. They are all listed here. That is in the first phase, distributor design, operation methodology. So here the operational reliability was established here. Then refractory lining problems were faced. Then improved refractories were installed. Then in phase 2, the optimization of parameters were attempted. And the operation methodology was thoroughly established here. In the third phase, elevated pressure operation, long duration operations were attempted, and new hot gas topics were implemented. So the complete aspects of operation and long duration operation, reliability, all those things were established in the third phase. Then, if you see the design and performance summary here also, could operate up to 9 bar per step. Then carbon conversion it was designed for 90. It could go up to 75 to 90 depending on the operating parameters. Then organic sensing could go up to 75 to 80%. And we could achieve a longest single run of about 204 hours. Here, basically being an R&D unit, we are not able to focus on operations because of limited manpower and expensive operational cost. So with all that limitations, we could even achieve some longest run of 104 hours. And the total plant has operated 2,500 total cubic hours of operation. The kind of developments we could achieve with this plant was totally designed in-house. Then this plant was established for the assessment of the performance of these gasifier and subsystems. Then to perform operations here, we concurrently have some old models for supporting these hot model studies. Then because of this combination of old and hot model studies, we resulted in development of gas stream distributor, fine cycle system, even operation methodology, process control philosophy. This fluid classification process, what kind of operating parameters have to be fixed, how to fix the process control criteria for operating this, for a temperature of operation, for controlling the fluid hydrodynamics. All these were done right from scratch. So all those things could be established. Then we could also develop capability for design and fabrication of this main process equipment and scale up commercial size planning. That capability would be established by operating this Hadoop plant. Then we could also establish optimum operating parameters and reliable classifier performance through these various facilities. Now the combined cycle plant this is the fluid bed classifier which was retrofitted into this existing 6.2 megawatt LCC plant. The picture is shown here. Now this is the flow scheme. This is the fluid bed classifier. The pole is spread right similar to the moving bed classifier. Here also pole is spread from atmospheric to high pressure through the lot of alignment. The rest of the is a gasifier. The air is drawn again from this gas turbine, and the steam is drawn from a three-story boiler here. This is generating steam through this recovery heat from the hot gas. The gas meter system is same as what was existing for a moving bed gasification plant. Gas meter system as well as these power cycles, gas turbine blocks and steam turbine blocks. They were all built in, which was existing earlier. Only the fluid bed gasifier was substituted in place of moving bed gasifier. Here also, it was designed to process 168 tons per day coal. This one at an operating pressure of 12.5 bar per step, and at a temperature of about 1000 degrees centigrade. And it was aimed to achieve a carbon conversion of 89%. Then under actual conditions, if you see, we could achieve 89% for this gasifier, but 88% is not enough to go for commercial size gasifier. So we incorporated some fine cycle system to improve the efficiency further. Now, this gasifier has been in operation since 1997 until date. So in the last few years, the gasifier was continuously operated, and the gas was supplied to the boiler plant furnaces for their use. So it was operating for about 4,000 levels last 2 years, and the gas produced from gasifier was given to a high pressure boiler plant. It has supplied more than 30,000 tons of gas to high pressure boiler plant. So because of this experience, gained tremendous experience in the continuous operation and the performance of this gasifier. The plant has logged about 10 right from because it started from 1997. So the total hours of operation is about 8,000 hours. The parameters are given here. That is, the gas plant was operated variable load condition to meet the demand of this high pressure boiler plant, and by varying this load, we also wanted to check the reliability of the system at varying loads. So the gas flow was varied right from 5,000 to 10,500 kg per hour. Gas pressure was varied from 3 to 7. Temperature from 9 to 1050. Calorific of gas achieved was right from 950 to 1050 kilocalories per normal temperature. So with all these variations, the operation could be established satisfactorily, and all kinds of operational parameters were established for a reaction code in this gas plant. Then, because the non-recycled system, we could achieve only 89%. Then, we thought of improving the gasification efficiency by increasing this fines recycling system. So, as I told you earlier, some gold model studies were set up in concrete facilities in Hyderabad. Also, the same thing was implemented in pilot field studies at Hyderabad as well as in teaching plant. And the improvement in carbon emissions would be seen in the next slide. This is a pictorial view of the recycle system installed in CCP gasifier. This is in a CABC boiler facility at Trichy. Now you can see the unbound carbon which is coming out in ash. In a non-recycling mode, we were getting about 18%, say 70 to 80%. Then after introducing this recycling, the carbon content came down to 12%, resulting in the improvement of carbon and overall carbon content up to 91 to 97. So, thereby increasing the coal gas efficiency also from 62 to 66%. Now, all these pilot plants, we could operate up to 10 bar pressure, and the gasifier dimensions, like one gasifier was having 200 mm diameter, second 450 mm diameter, third one the 6.2 megawatt diameter, the student gasifier had 1.1 meter diameter. So for scaling up for a commercial IGCC plant, you need a gasifier with a diameter of about 3.5 meter diameter. Then operating pressure has to be 30 bar pressure. Now, to know how a gasifier performs at that condition, 30 bar pressure, we didn't have any facility to establish, and it is very expensive, very time consuming. So we went in for establishing a high pressure thermogravity analyzer facility to generate data for high pressure gasification data. So this high pressure TGA facility was set up in Corporate Authorities in Hyderabad. This high pressure TGA can go up to even 70 bar pressure and temperature as high as 1100 centigrade. And here you can simulate both combustion as well as gasification reactions. So it has got typically, this one is a mini reactor. This thermogravity analysis is nothing but measures weight changes in real time. So what we do, you have a small sample of coal, you make char out of that coal, then a few milligrams of sample. You place it in this balance pan of this high pressure TGA. There is the thermogravity analysis is nothing but a combination of weight balance and a mini reactor. So the balance pan, you keep the char sample. If you want to conduct a combustion reaction, you pass air through that. If you want to conduct a gasification reaction, you can pass steam or carbon dioxide. Then the weight changes in real time will be recorded. and we can establish the kinetics of the gasification of combustion reaction using this facility at whatever pressure you want, at whatever temperature, at whatever proportion of the reactants. It can be used, the variations can be used and to generate data. This is a pictorial view of the high pressure DG facility which is set up in corporate organization in Hyderabad. This is the high pressure DG reactor. The balance is housed in the top portion of this system. Then this is the steam generator facility for supplying steam to DGA. This is the gas master cooler or condenser for condensing out the excess steam which is generated. Then if you want to conduct a CO2 gasification reaction, you can supply CO2 through gas cylinders. For oxygen-based systems, you can supply oxygen through cylinders and you can conduct your studies. Now, with the help of these instruments, we could conduct these kinetic studies for three gasification reactions. There is carbon steam giving carbon monoxide and hydrogen, carbon with carbon dioxide giving carbon monoxide, and carbon with hydrogen giving methane. All these three reactions were conducted in the high pressure facility and with following variations in operating parameters. That is, system pressure was varied right from 1.5 to 10 atmosphere and up to 30 atmosphere. Varied. Temperature was varied from 900 to 1000 degrees centigrade. Then reactant concentration was varied from 15 mole percent to 100 mole percent. And we could generate kinetic data for a variety of coals, high ash coals, pet coal, high sulfur coals, lignite. For all coals, we could establish the rate expression for various combination of operating conditions. For developing rate expression, the empirical nth order kinetics was assumed for these gasification reactions. The rate is in terms of this X is carbon conversion, the fraction of carbon being converted, and beta is the order of reaction. PA is the partial pressure of the gasification media like carbon dioxide, steam. So rate was generated using this empirical method of kinetics. Now, once we develop this kinetic data, and once we have experimental data from several pilot plants, a need was felt to develop a mathematical model to get this plant data validated with a model, as well as to predict performance for higher scale gasifiers, for other operating parameters, for various kinds of fuels. So it was felt a phenomenological model has to be developed to as a tool for predicting the performance for a commercial size gasification plant. So with that intention, the mathematical model was developed in parallel. The main features of those models were is a one-time steady state model. This phenomenological model incorporates, simulates the fluid bed hydrodynamics, it simulates the reaction kinetics, as well as this combustion and devaporization, cold combustion reaction and cold devaporization reactions are absolutely instantaneous in this model. So the model provides finally the specific gas yield and the gas composition, as well as the heat and mass balance for each stream as well as each component. So in this model, you can predict the gas composition and gas yield for any gasifier of any dimension, for gas with any type of fuel, provided you have the kinetic data of that fuel, it can predict. This fluid bed hydrodynamics, which was assumed in this model, has this two-phase theory of fluidization has been adopted for this model. That is, in a public fluidized gasifier, you will have the bubble phase as well as emulsion phase. Now, in a public fluidized bed, you need a minimum fluidizing velocity to fluidize any quantity in excess of the minimum fluid velocity will travel as a bubble. So anything in excess of the medium of level, anything in excess of medium of level will travel as bubble through the fluidized bed, and the fluid equivalent to medium of level will remain dispersed in the fluidized bed along with solids. So this is the two-phase area of fluidization proposed by Levenskill was adopted for this model. Then this shows how the model has been computed. That is, the model assumes a number of cells. In each cell first the gas phase processing between bubble phase and immersive phase is considered. Then the gas phase and reactions are considered for computing the product gases formed out of those reactions. Then the final gas from one cell will go to the next cell. So like that, subsequent cell will go, and finally the product gas will come out of this model. Now this was the flow chart. Probably you will not be able to see this entire thing. Here the inputs are these gasified dimensions, cold properties, air and steam properties will be the inputs. Then even like solid, bed ash properties have to be included. Then the model starts with an assumption of this carbon composition. It computes the fluid bed hydrodynamic properties like bubble size, bubble parameters, like bubble race velocity, all those things. Then it computes the gas rate out of gasification reaction. Then finally it computes the carbon conversion. Then compares with the gas to carbon conversion. If they are not comparing, then new carbon conversion is gassed and iterated until the gas to carbon conversion and the actual carbon conversion matches. Then after that it goes to heat balance iteration tool. Finally it comes out of that once everything converges. You can see in this chart the kind of matching we get between an experimentally generated measured gas composition and the model predicted gas composition for all the components. Like here for carbon monoxide, the model predicts about 17.3 and the actual thing is 17.2. Like that for each component, there was a close prediction. This is for the 6.2 megawatt CCTP plant. Similarly, for 200 mm NPTG plant also, the model was compared. The model predicted composition as well as the experimentally measured gas composition, they were close to each other. So the model was validated with all these pilot facilities. Now, once we have come up to this stage, we were ready to, BHL was ready. BHL was ready to propose a constitutional gasifier. Then, at that point of time, the government of India, the principal scientific advisor to government of India, he formed an R&D committee to assess the BHL technology. Then the committee consisted of members from the principal scientific advisor's office, from NTPC, from Department of Science and Technology, from CSIR lab, from DA, Department of Atomic Energy, and from BHL. So the committee also noted that IGCC with the precise flavor gasification is ideally suited for these Indian codes, and the committee should assess the BHL's plans and also formulate some scalar methodology for 100 megawatt plant. The performance parameters fixed by the R&D committee are given here. There is carbon conversion efficiency is about 85%, holding gas efficiency is about 71%, and gross IGCC cycle efficiency is about 39%, and the gas calorific value should be in the range of 1000 to 1100 kilocalories per normal cubic meter. Now, in order to evaluate our pilot scale facilities, a working group was constituted to participate in the planning trials, and then This one I will skip because it will come last. Now, the kind of studies which were conducted in a 200 pilot scale study with working group are presented here. That is, they conducted X-ray radiography studies to see the hydrodynamic characteristics of fluidized bed. Then, as part of this program, a radio-based study was conducted to assess the quality of fluidization in gasifier. Then, operating parameters like mean quantity size of the cold feed, operating velocity, steam to cold ratio, air to cold ratio, and bed temperature, all these were varied in their questions as recommended by them, and performance was shown to them in this small scale pilot facility. Then experiments were also conducted, that slide is not there. The experiment was also conducted in 6.2 megawatt IGCC with the participation of members of this working group and UTPC with similar kind of variation in operating parameters, and the operation was shown successfully to the. Now, I think time is going. The working group completed all these studies for recommending 100 megawatt time. That is, X-ray radiography studies. They developed an artificial linear network model with the help of this one. NCL Pune, National Chemical Laboratory, Pune. Then solid phase studies with the help of Baba sensor. Then gas-related experiments both in PFDC 200 megawatt facility as well as 6.2 megawatt conducted. In parallel, some mathematical model was also developed by NCL Pune. Then with all these efforts, basic scale-up criteria for higher size gasification plants, IGCC plants was evolved, and they submitted an internal report to the committee. The committee finally recommended that, concluded that the technical feasibility of upgrading the 6.2 megawatt IGCC to plant 200 megawatt was established. Then they recommended to prepare a detailed project report for 100 megawatt IGCC. And also the committee chairman also recommended a recycle system testing in CCTV plant. The same thing is coming from another scale I will show you. Now, if you see the scale-up approach adopted in DH we established our pilot plants. This one model was developed in parallel. Then kinetic studies were done using this high pressure TGA. Now, with that model was validated with the pilot plant results. Then that validated model with the incorporation of this kinetic data for high pressure operations. The model was again used for 30 ATA prediction because we didn't have the experimental facilities at 30 ATA pressure. We had to use the high pressure TGA data for prediction of gasifier performance at 30 ATA. That is how our scale-up approach was adopted, and the design was made for 125 megawatt IGCC and 180 megawatt IGCC with this approach. This is nothing but some of these operators. The kind of scale-up adopted here, both geometrical scale-up and pressure scale-up, was gone through in stages which is normally adopted by other technology developers elsewhere. And the total power series integration also was checked through a simulation study using Aspect Plus software. Now, this is the scale-up approach which is shown here. That is, we started from 200 from reactor at a pressure of 2 ATA pressure. Then scale up to say 450 ohm reactor 18 per day plant with an operating pressure of 10 bar pressure. Then 6.2 megawatt CCTV plant at 1.1 meter diameter with an operating pressure of 12.5. Then 125 megawatt at 30 bar pressure with a diameter of 3.1 meter diameter. Then 182 megawatt with a diameter of 3.5 and an operating pressure of 30 bar pressure. This is how the approach, scale approach has been adopted in BHEL. And the design for 125 gigawatt was vetted by a team of design review team consisting of Professor Boyd from Chalmers University, this one, Sweden, and members from IIT and MIT Trichy. So we also took external support from IIT Chennai and for CFD modeling of this gasifier. Then this is the current focus. That is, right now we are planning for this IGC system with the conventional wet gas cleaning systems. So here now the future for future IGC systems, medium temperature hot gas cleaning system is being developed. There is R&D studies have been made on the medium temperature hot gas cleaning system. Then hydrogen production from coal gas, reactivity studies for various Indian coals. Then IGFC system, that is integrated fuels gasification, fuel cell system for power generation. Then for basic engineering of this 450 megawatt commercial size IGC systems. This is as part of the hot gas cleaning systems of one project has been completed for medium temperature cleanup. This is our course with the BHEL which has been listed here. Kind of pilot scale process development, modeling and simulation, scale of methodology, and all these repeated already. And as a part of this commercialization initiative, we have supplied a process and engineering document for a pilot scale gasification facility for ESCOM South Africa. Then we have prepared a detailed technical report for 125 megawatt and 180 megawatt HCC plants. And we have set up an exclusive co-research center for providing analytical support to such a technical these advanced IGCC plants. To sum up, say coal will be the dominating fuel for the foreseeable future. BHEL has hands-on experience in designing, engineering, fabrication, direction and testing of both these of both unified and precise gasification system and their implementation for IGCC. So BHEL is in a position to commercially offer IGCC systems right now. These are some of the facilities have been shown in Nina. Thank you for giving me the
Thank you so much, sir. All of you to join the next session with the training call. Announcement to the participants. The next session is a group discussion on the topic creating a knowledge network for CCS and CCD in Indian Thermal Power Sector. Start by 1:55 p.m. I request all of you to assemble here by 1:50. I'm discussed in groups assigned to you yesterday. We'll be making the seating arrangements from that. Group 1, group 2, group 3, and we send here group 6. We'll arrange systems to identify your groups. And if you want to make PPT, you can just write it down and give it to us. We'll put it in the PPT. Or you can use the chat and mark us.
Grupo open pongo ni por dos.
you know,
for this training program. I understand it's been 3 long days where it's been packed with long sessions. This will be the last of it. So far, our experts have spoken at length about CCT in great detail over the last 3 days. And we have also discussed CCS and very particularly the capture aspect of CCS in great detail. However, CCS discussion would be incomplete without discussing the other 2 key aspects, which is transport and storage. So within the next hour, I will be taking you through transport and storage, or rather, each one of you will be taking all of us through these topics. I have a set of questions that I put up here. All of you all know the answers for all of these questions because you've been listening to the sessions over the last 3 days, and it's just a bit of, say, you could, like for example, when I say what are the possible modes of transporting CO2, just think about it for a minute, and any of you give me the answer. I'll put it down on the board here.
Pipeline.
Yeah, sure. I'll just give me 1 second. I'll brief you on the entire session and then we'll take off. So likewise, what we'll be doing is, you will be giving me the answers for all of these questions. So that ensures that you've had a quick recap of your understanding of transport and storage, and whatever gaps are there, we will bridge it through the PPT, because I prefer not to use too much of the PPT actually. So we'll start off with our first question. What are the possible modes of transporting CO2? Sure, sir. Pipeline. Anything else? What are the possible modes of transport are there for CO2?
Tankers.
Tankers. Excellent. Vessels. Any other perceivable mode of transport? Anything that comes to your mind? Compressors for transport. We are specifically talking about carbon dioxide has been captured, it has been compressed, it needs to be transported to its storage site. So, is there anything else that can fit in here? Or you think this is alright? This is alright, okay. What are the factors to be kept in mind while designing transport media? Now, exactly, we all know that we need certain transport media. Pipelines, tankers, vessels. Now think about what aspects have to be kept in mind while designing. Number 1. Safety. Leakage will again form part of safety. Anything else?
Size.
So size, the pipe diameter and size.
Temperature should be maintained.
Temperature should be maintained.
What form? Liquid gases.
That will be forms of transport. Okay, fine. You can say the form of carbon dioxide. Anything else?
Pipeline routing.
Okay. The layout. Pipeline routing. Anything else?
Selection of material.
Perfect. Selection of material. Actually, it's a it's probably the primary aspect that you take into account when you are designing any transport solution, be it pipeline or vessels or your tankers. The material that is used to build the transport media. Right. Do you think anything else can go in here? Or you think it's alright? Cost is again, it is at this stage of CCS development not a very important factor. But yes, once CCS sets out on a big scale, cost will then become a parameter. And that's when, that comes at a much later stage. Still put down cost. Put down cost. Right? So this is okay? Move to questions. What would be the possible implications of carbon dioxide transport? Say you're laying pipelines. or you're transporting via vessels or tankers. So what could be the possible implications of carbon dioxide transport? Okay. Safety aspects. Anything else? Any other possible
Quantity to be transported.
Okay. Quantity to be transported.
Implications might be more release of emission. How to transport? Storage should be there. Storage to transport.
Storage is obviously there. There is no question. Storage location is there. What I am asking you is, let me be a little more specific. The implications of transport on, say, other living beings on the earth. Or you could also say in terms of laying pipelines, for example, the routing of the pipeline, etc.
Layout is the implication. Backup system.
Backup systems. Alright, so this seems fine as of now? Okay. What we'll also do is we'll answer the other three questions as well on storage, and then we'll go to the presentation. Again, so what do you think are the possible storage locations for captured CO2?
Depleted,
You are supposed to answer.
depleted things.
Depleted mines? Right, depleted mines.
Depleted oil wells.
Depleted mines and oil wells. Underground. Right. Under the sea. Underground. Next one. Under the sea. Space. This is a very, very innovative answer. So this is something that we really have to probably, the scientists of the world have to work on this option, I guess. Space. Anything else? Limestone. Could you be a little more specific?
Some mountains in US and Canada where they store them.
That's right. Limestone is. Limestone is.
Because it is converted to calcium carbonate.
So you think so it could be stored over time. Just note it down. Limestone is. Any other possible storage locations for carbon dioxide?
Converting CO2 usable to
Okay. Converting to usable fuel. Any other possible storage locations where CO2 can be stored? That I think has been covered. Okay, fine, right? In other terms, take a hyphen, right? Between the rocks. No. Between the rocks. Okay, and? When you say concrete bunkers, again, anything more specific? Are you talking about bunkers on land, or are you talking about making bunkers under the surface? Underground bunkers. Okay, we discuss the storage aspect in a little bit. The bunker concept is coming up. Yes, underground bunkers. Concrete bunkers. It's actually a good idea, but yeah, it will come under intermediate storages. It cannot be permanent storage option. It is an intermediate storage option, but it's not a permanent storage option. It is definitely a media because it is an option. You're right when you said that it's an option. Right? Okay. How do you think the storage site can be identified? Just wild guesses. I mean, none of us are geologists per se, but yes. Sorry? No. What I'm asking is, suppose you decide that you want to store CO2 in some depleted oil well or something, some other underground area. How do you identify such sites? Just your thoughts on it.
Life is not supported.
Okay, where life is not supported.
It's not in the populated area.
Exactly. I see it. Anything else?
International model.
Okay. And model, how can you select sites?
Proximity to the plant.
Okay. Proximity to plant. And
Like desert, forest.
that is covered in area where light is not supported, etc. How do you know what is under the ground? Perfect. Satellite. Any other thoughts? Okay. The last question. What do you think the possible implications of large-scale storage of carbon dioxide? Implications of CO2 storage.
Earthquake might.
Okay. Earthquake. And other natural hazards. Anything else? Okay. So what we'll then do is we'll quickly go over the presentation and see how much of it you have got yourself right. Because this is a great job. You actually covered a lot of things comprehensively, which shows that you all have a very good understanding of what transportation and storage involves. That makes my job that much easier. So I'll quickly take you through a couple of slides and one or two good videos that we came across, so that helps you understand how the whole process happens. Thank you. From Mazda that captures, that talks about capture.
Audio is not coming, but let us explain on this. This is from the Emirates State Plan in Abu Dhabi, where you have 6 million ton state plan, which you can see on the violet color over there. And this portion is the DRI plan, direct reduction ion coming on. It's a gas-fired DRI where you get CO2, almost 95% pure CO2 is coming out. This CO2 is basically captured through the pipeline and then transported back. You can see the color over here. And this is the typical layout of the plant coming out. This is the CO2, this is the buffer tanks over there where we store CO2 and clean up the CO2. And after cleaning up and goes to the compressor house. And then from the compressor house, it goes to the pipeline. Actually, in this particular video, we are following the pipeline.
Could be pipelines, which could be both on the surface and also under the sea, tankers and vessels. As of now, pipelines are most cost effective as far as large scale transportation of carbon dioxide is concerned. And as of now again, considering current practices, the transportation conditions for CO2, it is very similar to any hydrocarbon transportation condition. Again, CO2 theoretically can be transported in all three forms, gas, liquid and solid. As of today, again, solid, it is not practical for large-scale CCS because the amount of energy that is required for the solidification itself is very, very high. So it is not economically, again, viable for large-scale CCS. So solid transportation is theoretically possible, but it is not a very economical option. And yes, volume of transport can be reduced by transporting at very high pressures, and that's usually what is, as of now, done. Somebody spoke about the design aspect. Somebody said that the material that is used for, preparing the transport media is very, very important. To be more specific on this, carbon manganese steel is usually used to make pipelines for rice flow transportation, as it is not corrosive. Here it is important that the carbon dioxide that is transported is free of NOx and SOx. Again, because the presence of sulfur can result in corrosion of the pipelines, because most of these pipelines are made of, say, stainless steel or other forms of steel. So it's important that the carbon dioxide that is transported does not have any sulfur content or NOx in it. Coming to the construction aspect of, say, pipelines on land, before any project proponent can set out to, lay pipelines and start construction activities for CCS project, all legal permissions and all clearances must be in place before you can actually start putting up the pipeline, because otherwise it results in right-of-way issues, and because land acquisition usually is a very big problem in case of laying pipelines on the land. Then usually the process is very similar to laying your hydrocarbon pipelines, as I said. Initially the trench is excavated, and usually they ensure that long lead time activities are done first. It is a very tricky part when you're trying to lay pipelines in densely populated areas or in river beds and small crossings, road crossings, etc. Because these are very critical areas, and hence and they also take the longest amount of time. So these are activities that are completed first, and then peripheral areas are taken on. Usually, again, as you say, if you've noticed any pipeline construction on the roads, you must have realized that pipes of certain length are welded together and then they are laid in trenches. And usually what happens is, once the pipeline is tested, obviously to ensure that there is no leakage, etc., that's happening through it. Not just hydrostatic tests, a lot of other tests are carried out to ensure that there are no cracks in the pipeline, so that we can be sure that carbon dioxide will not escape through any possible means when the pipeline is then put beneath the ground. So once the pipeline is welded together, as in the sections of the pipeline are welded together, and it is placed in its trench, the trench is again and it is sufficiently covered or insulated to ensure that there is no peripheral damage to it. The trenches are then filled, and in most areas vegetation is again brought back on the location where the pipeline has been. So essentially it is right beneath the ground, where patches of vegetation can be grown on top of it. There can be houses on top of it. It's quite possible. When it comes to underwater pipelines, I was trying to get a video of how it is laid, but unfortunately YouTube is having problems. Again, this is again very, very similar to any normal pipeline construction that you must have, if you are aware of, as far as marine construction is concerned, where again the commonly used method is the lay barge method, where pipelines of smaller lengths are welded together on the shore and then taken on the barge, taken deep into the ocean, and then it is placed on the ocean bed. Here again, either it is directly placed on the ocean bed, or trenches are dug if the ocean, if the water level is shallow enough, the trenches are dug and it is placed on the trench. Suppose if it has to be placed deep in the ocean, the trenching happens after the placement of the pipeline. Coming to operation and maintenance, this is probably one of the most important aspects of CO2 transportation. Because a lot of responsibility lies in the operation and maintenance, because once the pipeline is laid, it is very, very essential to ensure that it is in good health at all points of time, and it doesn't pose pose any hazard for the people who are living around or in the same area the pipeline is located in. Because oftentimes it happens that these pipelines can be very densely populated areas as well. So what happens is, the example that I put on the slide is typically a case of what happens in the United States, where a lot of small CCS projects are already functional. So the norms are pretty much the same across the world. Like for example, the key is manpower training. People are specifically trained on how to handle these CO2 pipelines. Also, timely inspections are carried out after the initial laying of the pipeline. And there is a sequential process, and there are various approaches that are there to ensure that the inspections are carried out, and we are assured at all times of the fact that there is no leakage or no other hazard because of the pipeline. Like for example, the first point that I mentioned, pipelines are cleaned and inspected by piston-like devices driven along the line by gas pressure. These devices, they are called PIGs, P-I-G-S. It's a small battery-operated piston-like device which is inside the pipeline, inside the CO2 pipeline. So what happens is it moves along the length of the pipeline, and it has dual functions. First, it cleans the pipeline to ensure that there aren't any scaling, there isn't any scaling. And secondly, it also inspects the inner lining of the pipeline to ensure that there is no leakage or cracks that are happening or any unusual formations in the pipeline. Secondly, these pistons, as I said, are multifunctional. They can measure internal corrosion, mechanical deformation, external corrosion, and precise position of line where there could be some kind of faults, etc. Apart from this internal monitoring, there are two other ways of externally monitoring these pipelines. Now, what happens is these pipeline sites are usually marked, and the people who carry out the inspection operations are aware of where the markers are. And usually the general public is also made aware of regular markings as to where the pipeline lies approximately. So what happens is, keeping the public aware of where the pipeline is ensures that they don't do any unauthorized excavations or any construction on the area where there could be a pipeline or in areas where the pipeline is not out of the ground. So this again is for their own safety. Several programs, I think yesterday Shweta had shown one video where they had shown people explaining to the locals about these pipelines, then sensitizing them about the transport pipelines and what are the do's and don'ts as far as these pipelines are concerned, especially in areas where they are populated. Now, there are two ways of monitoring these pipelines from above the ground. First is, there are again battery operated, you can't call it a helicopter, it's a small probe-like thing which is again battery operated and goes along the length of the pipeline. So these again work on infrared principle, wherein through infrared rays they detect for leakages and possible sources of deformation or any unnatural activity as far as the pipeline is concerned. Also, aerial helicopter surveys are undertaken by officials to ensure that there is no unauthorized excavation, digging, or any such thing that is, or any unauthorized construction that's happening on top of the location where the pipeline is, so that it doesn't damage the pipeline in any way. It could happen that somebody is not aware that the pipeline is laid, they may start digging and they may hit the pipeline, and it can be fractured. It is quite possible, and if that happens, it can prove to be a big disaster. So. Usually officials carry out timely inspections to ensure that no such activity happens. Underwater pipelines, they are again monitored by battery operated vehicles, small submarines that go along the length of the pipeline to monitor the surface of the pipeline. And as I said, public education and communication is the absolute essential thing, because it is important to sensitize the locals about what's happening around them. Facility security and leak detection. This is again taking it to another level where some pipelines have independent leak detection systems. It could be through various ways. One of the options that I told you was through the battery operated ones. It could also be due to it can be acoustic measuring systems, etc. as well. And again, before granting license to operate a CCS plant, set of emergency contingency plans are laid down, which are reviewed by the regulatory authorities before granting the license to operate a CCS pipeline. The table that we see in front of you is a methodology that's developed by the Intergovernmental Panel on Climate Change, IPCC, and it is a methodology for future monitoring, verification and reporting as far as CCS projects are concerned. Again, going into a little more depth on this, the first point talks about site characterization, where they say that the project proponent has to confirm that the geology or storage site has been evaluated and that local and regional hydrogeology and leakage pathways have been identified. Which means that before you start out on a CCS project, the site that you have identified should have been thoroughly evaluated and the findings have to be reported. Secondly, assessment of rise of leakage. IPCC says the participant, proponent has to confirm that the potential leakage has been evaluated through a combination of site characterization and realistic models. Again, when they say based on site characterization and realistic models, they are saying you have to predict the movement of the carbon dioxide over time in locations and identify possible locations where leakages or emissions of carbon dioxide might occur from the storage sites. Monitoring. This is to ensure that an adequate monitoring plan is in place and reporting. It is also, the proponent is required to report the amount of carbon dioxide that is injected at all points of time and any emissions from any of the points in the storage site. This is to ensure that a robust monitoring verification system is in place and there isn't any chance of leakage, and if any leakage is identified, it can be arrested or measures can be taken immediately. We then discussed about vessels, as somebody rightly pointed out, as for carbon dioxide transportation. This technology as of now is at a very, very nascent stage, and again what happens is to take the carbon dioxide from the source, say a power plant or a steam plant, to the dock, you require tankers for this purpose. And again, these tankers can be similar to your hydrocarbon carriers.